This playlist deals with some aspects of Eurocode 2 version 2023. Watch this playlist for further selected topics. It deals with clause 9, serviceability limit state, and it's about minimum reinforcement, crack width control, part 4. In section 9.22, we have discussed the minimum reinforcement needed to avoid yielding. And we did that until now when there is no crack width specified and the steel stress was equal to the yield stress of the reinforcement. Now we will handle the case where the crack width is specified, and it means that the steel stress is less than the yield stress of the reinforcement. For this, we can look into Annex S, and in Annex S Part S3, they talk about minimum reinforcement areas for crack width control. Now, this is confusing because sometimes in Chapter 9, or in Clause 9, they use the term to avoid yielding, but in Annex S, they use crack width control. In Eurocode 2 2004, we talked about minimum reinforcement for crack width control. So I strongly recommend to get rid of this term to avoid yielding, because I still don't know what it means. So you should replace it by crack width control in total. So Annex S, it states that unless a more defined calculation shows lesser areas to be adequate, the required minimum areas of reinforcement to control crack width may be calculated as follows. And then there is a text, which is exactly the same text as in 9.22 part 2. And then in Annex S, it says, in addition to the requirements of 9.22, in addition. So you have to fulfill both. You have to fulfill 9.22 and you have to fulfill the conditions in Annex S. The reinforcement necessary in the part of the cross-section under consideration may be determined by formulas S1, S2, and S3 as appropriate. S1, again, is for only bending, S2 only tension, and S3 is for combined axial force and bending. This is not consistent. 9.22 deals with minimum reinforcement to avoid yielding, and the text is confusing because 9.221 is the reinforcement needed to withstand the cracking bending moment. But the reinforcement needed to cracking bending moment means that when the bending moment on the section is the cracking bending moment, the crack width is 0 by definition. Because when the bending moment is smaller than the cracking bending moment, you cannot calculate a crack width. So now it's a little bit confusing because this is the minimum reinforcement to crack width control, where you specify a crack width, and you have to fulfill 922, but in 922 you cannot calculate a crack width. That's not possible. So it's not very, very consistent. It's not very clear. We will see what this will imply and what was the intention of Annex S. In fact, it's simple. Annex S is the minimum reinforcement for crack width control with a specified crack width. And 9.22 is the minimum reinforcement for crack width control, not to avoid yielding, but for crack width control with no specified crack width. Then at that moment, it is clear how to cope with this. First, we will tackle pure bending. In pure bending, we must apply the AS minimum W2 is of course 0. we must apply formula S1, which is this formula here. And we have seen in the previous video formula 9.2. So you have to comply with both. The minimum reinforcement must always be bigger than the one from formula 9.2. In the formula S1, you see FCTF, which is can be taken as FCTM. We know now already this formula. And KH here in the formula 9.2, remember, this is the formula of KH. AC effective is the area of the part of section under consideration. That's what they say in Annex S. Nothing else. No reference is made, nothing else. Just is the area of the part of section under consideration, which is wrong. Because AC effective is not that, not at all. So we assume that AC effective is the same as defined in 9.3. It is not stated in S3, but we assume that. So we should add this to be clear in the formulation. Then we can have some remarks to make things a little bit clear. When do we use AC, which is the concrete section, cross section? And when do we use AC effective? Why is there a difference between those two? Well, the idea behind it is that you use the full concrete section together with the tensile stress in the reinforcement equals to the yield stress. You do that for the first cracking. It means it's reinforcement to avoid crack locations of localizations. And it's a full concrete section. The subsequent cracks, the cracks that follow on, then for those cracks, only the effective area around the tensile reinforcement needs to be considered. So then you use AC effective with a steel stress, which is of course smaller than the yield stress of the reinforcement. So that was the main idea. First cracking, you have the full concrete section. Subsequent cracks, you have the effective area around the tensile reinforcement. The AC effective is then defined not by a formula, but it's defined by picture, by a figure, which is quite annoying. We assume that AC effective equals BC effective times AC effective. It's just an assumption, it's not in the code. Then you have on the left-hand side, they say it's for a group of bars, and the second picture is for isolated bars. And then you have for circular cross sections for bending. We will not look at this in this video. We only will concentrate us on a group of bars and isolated bars. The definition of AC effective, you cannot program a picture. So you need to resolve it by formulas. In the Eurocode 2 2023, there are some formulas for HC effective, which is the effective depth of the section AC effective. And it's defined as the minimum of AC effective 0. I will just show you what this is. H minus X and 0.5 H. That AC effective must be smaller than half of the section. That's clear. That's obvious. For bending, we are talking about bending here. And HCF0, you will see it just now. This term H minus X, which is X the height of the compression zone. Now, how to calculate the X? How do we know under which condition we should calculate X? Under which bending moment we should calculate X? So this is not very clear, and it complicates the formulas. But H minus X is almost never, or you can neglect this term H minus X. It will not determine your AC effective a lot. Only when you have a large compressive force, then this can be important, or just not important, because X is then very, very large. Only for, yeah, then it can be important, because we are looking for the minimum. So when X is equal to H, when the whole section is under compression, then H the effective is 0, which creates a problem for the formulas. So that's why we will neglect this H minus X in the cases that we will treat. For n layers of bars separated SY is indicated on the drawing, HC effective equals this formulation, and HC effective 0 is the minimum of 3 terms. And AY is the location of the most tensioned reinforcement, the first layer of the most tensioned reinforcement. That's AY. The definition of HCF0, that's something that I've added to make the formulation a little bit more reasonable. Otherwise, it's getting complicated to read the formula correctly. So you see that HC effective 0 has a minimum of 3 terms. And this is a difficult formula to use in a general formula for minimum reinforcement. AY, we will, in what follows in the video, we will use AY for a single layer of reinforcement with the same diameter phi. Otherwise, if you have different diameters, you should a diameter phi equivalent and so on. It complicates the matter a lot. So we'll use this most common case of the definition of AY. Now we will look into a more usable formulation than this. For a circular section, it's equal to AC effective is equal to AC effective 0. So we forget about the circular section, and we will concentrate ourselves on a rectangular section, and on, in fact, this is more or less for beams, and this is more or less for claps. It's not the case, but it looks like it. This is where BC effective equals B, and this is where BC effective is smaller than B. So we assume one layer of n rebars diameter phi, and AY is equal to this formulation. So we will neglecting H times X, and then the formulation can be rewritten in the following more programmable, let's put it this way, formula. HE effective must always be smaller than H over 2 and is equal to this value for AY smaller than 2 phi, and so on. And I got 3 conditions. It's exactly the same result as what the previous formulas on the previous slide are shown, but this is more easy to handle, because now you can see if you choose phi and C and phi B are most of the time known, but you use phi, then you calculate AY, and then you see immediately in which condition you are, because phi and AY are now known, and then you can see in which condition that you can apply. This formulation is not in the code. It's something that I developed, so be careful of that, but it's much easier to use. AC effective is BC effective times AC effective. Again, this is not mentioned in the code. You will not find this formula in the code, or I didn't find it in the version that I had. Now we look at one layer of n rebars diameter phi, and S is the center to center of the rebars. When you look at beams, you will see that the center to center of the rebars is, of course, the total width minus 2 times AX. Now, we assume here that AX is equal to AY. It means that the concrete cover is exactly the same at the bottom as on the sides of the bar, which is not always the case, but in most cases it's like that. So that's why the distance S is B minus 2AX divided by N minus 1. N is the number of rebars. So A equals AY. And BC effective is then equal to, because there's no formula at all in the code for BC effective, not at all. So you have two conditions, AX smaller than 5 times the diameter and AX bigger than 5 times the diameter. And then for AX smaller than 5 times, this is the formulation, and this is the formulation. It's not simple, but at least you have a formula. The code does not specify a formula, only a drawing. For slabs, then the center to center of the rebars is 1000, it's 1 meter divided by the number of bars, rebars, and BC effective is then much simpler, is then the minimum of 10 times N times V, or B, the minimum of it. Now, all those different conditions are very confusing when you are confronted with it in the first time. So what I did now is I made different drawings to explain you all different conditions. And the first is that when AX is smaller than 5 times the diameter, AX is the distance of the rebar, center of the rebar, to the edge of the concrete section. And vertically, it's AY. So when AX is smaller than 5 times the diameter of the bar, and the distance S between two different bars is bigger than 10 times the diameter, then you are in a situation where the red squares, the summation of the red squares, are AC effective. The next case, when AX now is bigger than 5 times the diameter, and S is still bigger than 10 times the diameter, then you are in the situation where the rectangular, which is AC effective, and the summation of all those red rectangulars, you are in this situation. So you compare this, and you see the difference between the two cases. Or AX can be smaller than 5 feet, but S is smaller than 10 feet. Then it's obvious that when S is smaller than 10 feet, then all those red zones are overlapping. And that's the case that you have in this drawing. And you can also have when AX is bigger than 5 times the diameter. So it means that here there is an area which takes not part of AC effective, but the areas overlap. Then you have this case. Now I hope you can appreciate that if you want to calculate minimum reinforcement, you have two parameters: the amount of diameter, the amount of rebars, and the diameter of the rebar. And depending on those two, you have different conditions to calculate AC effective. So you have a lot of combinations to calculate to find what is the minimum reinforcement, because you don't know in the beginning what diameter you need and how many bars you need. Now, I leave it to you to calculate what it will be, all the different combinations that you can make for different diameters in one layer. For instance, the first one is in diameter 12, the other one diameter 10, or diameter 16. Try to find out all the combinations that you can make. And then you can do the same exercise for 2 layers of reinforcement, which makes it more complicated. So now we have the formulation of the minimum reinforcement. First part was for formula S1. The second part was formula 9.2. And we will look now at the formulation for of the formula of S1, and we see that there is something appearing, which is H minus HC effective divided by H. We can now look at an uncracked section under bending, pure bending. You will see that the most tensile reinforcement, that at the outer fiber of the concrete, you have FCT effective or FCTM, and the zone around the tensile reinforcement the depth is AC effective. And then you will see that on the top of this zone AC effective, you have sigma, it should be read sigma CT minimum effective. So this is sigma CT maximum effective, and this is sigma CT minimum effective. So you have a block of stress, tensile stress around the reinforcement. The mean tensile stress in the concrete around this reinforcement is then very simple, the summation of the two divided by 2. And I put it equal to KFL times FCT effective. This KFL is a proportionality of FCT effective, nothing more or nothing less. We can now calculate how the value of KFL by just making with triangles, equal triangles. It's not that difficult. Then you see that sigma CT minimum effective is equal to this coefficient times FCT effective. Now we can compare those two formulations, and we see that KFL or K flexure or whatever you can call it is equal to this formulation. We can now make a quick check for bending, and then XE is more or less equal to H over 2. In fact, XE is a function of the reinforcement, so it's getting very complicated because the reinforcements you are calculating is also in the formulation of XE, but most of the time XE can be equal for bending, for pure bending, to H over 2. And then you see that KFL equals H minus HC effective divided by H. And this is exactly this term which is in the formulation of S1. So now you know where the coefficient is coming from. For tension, you can make a similar drawing, but then it's easy. You can see for tension that the AC effective zone, that sigma CT mean, the mean value is of course equal to FCT effective or FCTM. So to recapitulate, the mean value sigma CT mean, the mean value of the tensile stress in the concrete is proportional to FCT effective. FCT effective in general is this formulation. And now we can check for tension. Of course, for tension, XE is infinity. And if it's XE infinity, then KFL is 1, which is correct because we can see it here. It's 1. And for bending, then XE is H over 2. And AC effective is, of course, H minus XE. Then you see KFL is 0.5. So this is the general formulation of KFL.